solar system peculiar motion between the echo and the flame. According to the cosmological principle, an observer stationary with respect to the co-moving coordinates of the expanding universe should find the redshift distribution of distant quasars to be isotropic. However, the observed redshift distribution in a large sample of 1.3 million quasars shows a significant dipole anisotropy. A peculiar motion of the observer could introduce such a dipole anisotropy in the observed redshift distribution. However, the motion inferred therefrom turns out to be not only many times the peculiar motion estimated from the anisotropy in the cosmic microwave background, CMB, but also nearly in a direction at a right angle. The solar peculiar motion, in fact, turns out to be quite unexpectedly in the direction of the galactic center. Such a statistically significant discrepancy in peculiar motion, derived for different methodologies, could imply a violation of the cosmological principle, a cornerstone in the foundation of the Standard Model.
Sure. That's a lot of jargon.
Imagine that's a lot of jargon. Now, who exactly just said all that?
Who?
I don't know. I'm going to bring me here. This is Shen. So, hi everybody. And without further ado, since typically I start talking about the show, but we can't do that right now because the embodied voice in the background has already spoken. So, therefore, he must be introduced. So, who is this guy?
What up,
and you're
Shen?
muted.
I'm not.
What
I'm
up?
not moved.
What
Yep.
up, Doctor of Love? So, as we all know, people who watch the show, at least 50% of the reason is to see the Doctor of
Absolutely.
Love, right? So, there you go, with a title like that, you know, who can resist the urge just to just to see your headband and you, but. In all seriousness, though, yeah, it's been a little while since we've done a show. So
Yeah, life gets in the way, doesn't it?
It does get in the way, that's for sure. And been playing, for those of, I mean, the audience don't need to know this, but we've tried to coordinate a few times, but things were not able to fall through, but glad we're able to do it today. It seems like this might be a weeknight, might be a better night for both of us, so we can see how we can do that. Before continuing, let's just say for our viewers, if you've seen this episode, if you like this episode, or if you've seen other episodes and you haven't done so already, please like, subscribe, and share. If you're watching this, obviously you know that this is part of hopefully you know this is part of a longer playlist of shows, which we're trying to do at a cadence of every week if possible. Although, like I said, for this one, it's been about a month or so now. Today, we are talking, this is episode 232.
We've done 200 of these, over 200.
Yes, and if you can believe it, I still can't believe it. Who would have thought?
Right.
So with all that said, I'm going to leave some tickers running on the bottom, thanking various people who have supported, the show via donations or just letting people know, or just following us on Patreon, which is great. So with all that said, let's talk about the solar system peculiar motion. I read a little bit from the abstract of a paper, which we're going to talk about. But before diving into the paper, let's provide some context. So clearly, for instance, the solar system is moving. There's something known as the cosmic microwave background. The cosmological principle. All these terminology may be foreign to our viewers. So what does it all mean?
Well, yeah. So I came across this paper. I don't even know where I saw it, but we'll get to that in a moment. But so there's this like mystery of motion, and I like to start with a simple idea that everything is moving. So we know the Earth spins once a day. It circles the sun once a year, and then the sun in turn orbits the center of the Milky Way. And that's a journey that takes 230 million years. So all of those things are kind of, I guess, are familiar to us. We learned in school. but
Yeah.
yeah,
I mean,
yeah,
most of us, I think, in school have learned that the Earth is rotating like every 24 hours or so, one
right.
rotation a day, and have learned also that, at least in modern times, that hey, we're going around the sun, we're revolving around the sun.
So it turns out that the galaxy itself is moving, and so are all the neighbors in our local group. And so we're not just floating in some quiet fixed part of the universe. You might say we're plunging through it. So that motion, that's what astronomers call the peculiar motion. So it's not peculiar. Um, I know an unusual word to use, but so it's not strange, but it's because it's like peculiar to us. It's motion over and above the general expansion of the universe, and it raises a subtle but very deep question. Peculiar motion relative to what? What exactly are we moving relative to? And so a lot of us sort of think, well, we're just moving relative to space, but we can't just say we're moving through nothing. So in physics, motion is always relative to something. So a car moves relative to the road, a plane moves relative to the air. And so what is it that we think of as what's the air of the universe, or what's the road of the universe? And so for a long time, scientists assumed there was no such reference frame, so that in other words, there's no cosmic signpost that could tell us we were in motion. But by the time of the middle of the 20th century, we kind of discovered one, and it wasn't any particular point, but there was this faint uniform glow of microwaves that are coming from every direction of the sky. And it really was a remnant of the Big Bang itself. It was sort of proof that there was a Big Bang, and this is what we call I guess I guess our audience has heard of the cosmic microwave background. Or so we can refer to that as, sometimes you'll hear us just say CMB for short, cosmic
Realized I was
microwave
muted.
background.
We did have an episode prior about the cosmic microwave background.
Yeah.
I'll
So
post a link in the
that's
chat, but continue.
right. So this is so that's fairly extraordinary. It means in every direction we see this background um, uh, radiation, and we can measure our motion relative to it. So one of the first order effects of the measurements of the CMB is a large dipole element of it, which is singular and easy to remove numerically, but it corresponds to our peculiar motion relative to the CMB. I think people understand that. I don't think that's a complicated thing to.
When you say dipole, I don't. What does that mean? Maybe explain
Well,
that.
well, the way we measure velocity has to do with this thing called Doppler shift. So Doppler shift is this common experience, and usually in physics class, we learn about the when a source of sound, for example, is approaching us. It sounds higher pitched, and then as it passes by, it goes to a lower pitch. And I think probably everybody has experienced that when a train passes, that it sounds high pitched as it's approaching, and then as it's receding from us, it's lower in frequency. So light does the same thing, and in particular, the cosmic microwave background has that as a first order effect on what's seen.
Look at that. I mean, I just put.
Oh, you found it.
I mean, I found one picture.
Well done. Well done.
Yeah.
So this is the thing that pops out at us right away, is that there's this direction, and it's related to the direction of what our peculiar motion relative to the cosmic microwave background, right?
So in this picture you see here, like I guess we're headed towards the red part.
So
371 kilometers per second.
Yeah. So interestingly, the picture is kind of reversed relative to what we think of as red shifted and blue shifted. If it is so, and that's actually something that that I was able to correct in the in some of the literature is that even though the area that's red is the direction that we're traveling, and the direction that's blue is the direction that we're receding from. This is a particular kind of map projection. I guess most people are familiar with something like this. This maps every point on the sphere to this oval-shaped projection. So really, you can see that the direction that we're traveling is toward that point that's marked red in the picture there. So that might have been the end of this story. But it turns out, first of all, let me back up. Let me make sure that we're on a common ground here. When we measure this velocity, and I mentioned what they call CMB dipole. Dipole is a mathematical expression for how the velocity components distribute along the direction. I don't think we need to go into it any more than that, except that it's a mathematical expression. So
yeah, I mean, we're not necessarily diving more into math here. But in this diagram, can you explain a little bit about what, so we mentioned dipole, we're going from blue to red, Doppler shift, that's how we measure velocities. What is this purple line that says ecliptic?
So the ecliptic is the reference frame that we think of in terms of, and it's if the Earth were fixed relative to an inertial frame, then the equator would correspond to the ecliptic, right? So it's just a reference frame.
Gotcha.
So there's nothing particularly mysterious about that. Anyway, when we measure our motion relative to that background, we find that we're moving toward a particular constellation, and the speed is on the order of I think 370 kilometers per second, which is a good clip there.
Is this? Oh, sorry. Go ahead. I'm not going to interrupt.
Yeah, I don't. Yeah. So there's a peculiar motion relative to the cosmic microwave. So if you picture the universe. So what is the cosmic microwave background? So if you think about when the universe was just newly born, it was a hot, dense, full of charged particles and radiation that were all tangled together. Sometimes we think of it as a quark gluon plasma. So in that early fog, the light couldn't travel freely; it scattered constantly off of the electrons. But as the universe expanded and cooled, the atoms began to form, and then at a certain point, the electrons and the hadrons, notably protons and neutrons or hadrons, condensed, and so then the universe became transparent, and that's the moment that we experience as the cosmic microwave. It's like there's a surface where the universe suddenly became transparent, and so behind that it's the universe is scattering light constantly. But so as it cooled, then you might say the fog cleared, the light was set free, and that's the first burst of light that was released when the universe was about 380,000 years old, and it's been racing through space ever since. So that's what we see.
That's the furthest back we can see with an optical telescope.
With optical or radio wave or anything like that, we may be able to see behind it with gravity waves, which is an area of research. We still detect it today, stretched and cooled by cosmic expansion into a very faint glow that's all the way down the microwave part of the spectrum. So television, like in the old days when we used to have broadcast television, you'd see static.
This is an example of what the Doctor of Love. Okay, I'm just gonna call you Leonard. What Leonard was saying You can, obviously, when you look back in space, since light takes time to travel, you're really looking back in time as well. So the biggest telescopes in the world, like for instance, like we can see all the way, like the furthest back you could possibly see is a cosmic microwave background because that is that wall of radiation.
So that's exactly right. And I was about to say, if you could tune an old TV station to static, a tiny fraction of that static is part of that ancient light that's been greatly stretched out because of cosmic expansion. And so we kind of I like to think of this as the echo of the universe, or the echo of a flame.
Universe.
Right, echo of the
how
flame.
Poetic.
And the afterglow of the Big Bang still whispering across the cosmos. Okay, so here's.
I sound like you're about to write a poem or recite a poem, but let's continue.
No. So what's really remarkable, this CMB. So let's just talk about it a little bit. I think we have time. The CMB, and we've mentioned it before. It's almost perfectly uniform. It seems to be this at the same temperature all over to 1 part in 10 to the 5th or 10 to the 6th in every direction. There are some small variations that are also interesting in their own right. But it doesn't. So it's so astonishingly smooth and balanced. There doesn't really seem to be a preferred direction. There's no up or down, but as I say, not absolutely perfectly smooth.
Like this picture is depicting the temperature,
right?
With three different stages of I guess telescopes. So you can see that.
These are satellite based observations in the microwave spectrum, and so these variations are an area of intense research and study, and the undulations and variations that we see there are consistent with scales of the universe having to do with dark matter and so forth. And you can see as time has gone by, our resolution has improved. But what you're seeing here is the residual background minus the dominant picture, which you don't actually see here, is that dipole field that's related to our motion, our peculiar motion relative to this surface. I guess that's clear. So so generally one side of the sky looks just a bit warmer than the other, and it's about 3,000th of a degree Kelvin. And so that tiny difference is due to our own motion. And I want to emphasize that in this picture that you're showing here, Shen, we don't observe that here. It's been removed. So, but
this is just showing the what is it? I guess this is the residual temperature of the inhomogeneities, and this is an area of research. Has to do with to not confuse our audience. This is not the same as what was depicted earlier with the blue and red, which was showing the dipole in terms of the.
I think we're clear about that. I think we're clear about that. So one side of the sky looks a bit warmer than the other, and that's due to our peculiar motion. And it's about, what did I say? I think I said 370 kilometers per second. That's what's been estimated.
That's what you indicated.
Right? And we measure this through what's called the Doppler effect. It's the same principle that makes us the train pitch when it's passing change as it passes, but it's attributed to is an attribute of light instead of sound wave. So from this small temperature difference, the scientists can measure our motion with exquisite precision, and so why is that so stunning? So the Earth, Sun, and our entire solar system are moving at about 370 kilometers per second, which is 800,000 miles per hour, and we're going toward the constellation Leo. I have to tell you, I'm not sure I could find Leo in the sky. But
That's fine. I mean,
you know,
you know.
so the motion defines this is our peculiar velocity relative to the cosmic microwave. It's our speed through the ancient light of creation. And for decades, it's been accepted as the ultimate reference frame, the nearest thing we have to an absolute rest in the universe. So if you could drift at rest with respect to the CMB, the microwave sky would look perfectly even, equally warm in every direction. So we wouldn't see the dipole character. That's what makes that CMB so profound, is it just doesn't tell us where we are. It tells us how the universe began and how it still surrounds us. But it also sets up a puzzle, because when we measure our motion in another way, and that's the subject of this paper that I came across, it's not through the ancient light, but through the distribution of galaxies and quasars. The results don't match, and they're very far off. It's as if the early universe and the modern universe don't agree on which way we're moving, right? So that's where that's where this story kind of deepens. Okay, and so let me talk about, if I could, about the quasars. All right, so quasars are they belong to the universe, and I wanted to talk about them as the flame,
I wasn't
as
quite
it were.
sure if I was even pronouncing the word right, but quasars.
So
All right,
quasars are things that I read about when I was young, and I remember them. They weren't really what? So they weren't understood very well. They were known to be producing more radiation from these distant objects called quasars than whole galaxies, right? And so in the past 25 or 30 years, they've been determined to be supermassive black holes that are surrounded by swirling disk of gas and dust. We know that almost every galaxy has a very supermassive black hole in the middle of it. And quasars are believed to be, in the early part of the universe, a manifestation of a phase of the universe's evolution where quasars were burning or absorbing the swirling disks of gas and dust, and that in the more recent the contemporary epoch that we exist in, the quasars are not present anymore, but we still see them as they were 10 billion years ago. So basically, a quasar is the blazing heart of a galaxy. It's believed to be a supermassive black hole surrounded by all the gas and dust that's condensing and spiraling into the black hole, and creates tremendous amounts of, well, actually unimaginable temperatures, outshining billions of stars in the host galaxy. This was a big mystery,
is this a fairly accurate depiction of what a quasar looks like?
Well, I guess so. That seems. I mean, it's an that's an artist's depiction.
Yeah.
But I remember reading about this as a young adult, and before it was really understood. And it's a very profound fact that these things are producing thousands of times more luminosity than can be accounted for by.
And this is like in that evolutionary observable universe diagram here. So I guess they were extremely popular from 8 billion to about 12 billion years ago.
Yeah, I'll tell you, this is a really good chart that you're showing here, where our local neighborhood, right where we are, and our local neighborhood is the entire Milky Way, which gives you an idea of the scale of this. And so all of the galaxies are in a kind of like a shell, and then the quasars are in yet another shell. So what the subject of this paper is, that the quasars are not part of the modern universe. They belong to its like adolescence, right? If that makes poetic sense. Do you like?
Yeah, I mean, like the modern universe, or modern relatively speaking, I mean, it's only like the Milky Way. It's like the blue part, the furthest blue part down there. We're only seeing the modern universe we can see is only a tiny fraction of the whole universe.
Yes, that's right. But
So
because these quasars are so distant, they're distant, but they're not as distant as the cosmic microwave background. And
mhm.
so one of the principles, of physics is that, everything is the same in all directions. So we would expect that
Anisotropic, that's a word, right? And
isotropic. So
isotropic. Wait, what's the other one?
and
Anisotropic?
and and
Sorry,
isotropic, not
anisotropic.
isotropic, not isotropic.
Oh, and
Uh,
anisotropic.
anisotropic,
Anisotropy is not, it means not isotropic.
not uniform, right?
Okay, oops, sorry.
So,
Okay.
in the early part, and so what we were talking about earlier was that the cosmic microwave background, we had a peculiar velocity relative to it. And so the expectation is that if we were to measure, we can observe these very ancient, 10 billion year old quasars. They present us with a population that we can similarly measure our uh,
Yeah.
our velocity relative to, because it's like a shell of objects, and actually millions of these quasars have been cataloged, and so each quasar's light is sort of stretched or redshifted in the same manner that you expect we see with the cosmic microwave background. So our expectation is that we should not be we should not see a different velocity relative to the quasars as as contrasted with what we see with the cosmic microwave background. And so there's been millions of the quasars cataloged, and somebody went through the subject of this paper, was they went through and they did a survey of all of these quasars and determined us a a a peculiar motion relative to the quasars. And it turns out that it's dramatically different, and that's a big problem for us. So let's put it this way: if the universe were a vast ocean, the CMB would be like the motion of the tides, underlying swell of the cosmos. The quasars would be floating in it, and we're like ships riding that tide.
Right. And you expect the waves in the ocean and the ship's motion that is riding the waves to be in the same direction.
Yeah, so we expect them all to be kind of connected together, and that if we have a peculiar motion, then if we have peculiar motion relative to the CMB, then we should see that same peculiar motion relative to the objects that are floating in this in the sea, right? And but the trouble is, this data don't suggest that they don't, and that they're way out of sync. And it's not just odd. It's a potential crack in the foundations of the cosmological model, what we sometimes call lambda. Yeah, lambda cold dark matter assumes that on the largest scales the universe is uniform and isotropic, right? So there shouldn't be any special direction. There shouldn't be any cosmic currents. So if the quasar and the CMB dipoles disagree, it could mean something profound. And so either we've misunderstood the data, or the universe isn't as smooth and well behaved as we thought. It could be that local gravitational flow, maybe nearby superclusters are distorting our view somehow. Something is happening that we don't we don't understand. Or maybe the universe on the largest scales have subtle anisotropies, like a preferred direction that hinted something beyond our current understanding.
Right. So
Yeah.
I mean, you summarized it pretty well, I suppose, but like
Yeah. So let me.
this graph and okay, go on. Sorry.
Yeah, I was going to say maybe you could maybe I could share the screen, one of my screens here, because
You do what you got to do.
wait a minute, you got to do what I got to do what I got to do. Let me see if I can.
Possess a
This is.
screen.
Oh, you have it there. Okay.
I
Right.
mean, I have the
Okay.
article right here. I don't know
That's
if
the
you can-
article. This is
Yeah,
exactly
yeah.
what I wanted to show.
Yeah,
All right.
this article, for anybody who is interested, which I assume you are if you're watching this,
Yeah,
You can
maybe
find
we
it
should
here,
post that.
arcciv.org/abs//
Hmm
2508.20769. It's a Cornell University's research database, which tends to have
Yeah,
a lot of these research articles. So,
yeah.
anyways,
I'll be back.
okay.
Just a moment. Here we go. So actually, yeah, this is what I wanted to show. And so you see the red, that red area is the direction where we're traveling toward, and the blue is where we're traveling away. So it literally does not map to a red shift or a blue shift, which I thought I wouldn't have done it that way, but that's how these authors elected to show it.
Okay.
So to be clear, in this map, the colors don't literally mean red shift or blue shift. In fact, they're the opposite of of that paradigm. So the author used red to mark the direction of our motion. Okay, and so that's
So wait, in this diagram, is it similar to the other one, or I can't remember? Like, which way are we
no,
going?
this is um
Oh wait, this is the opposite of the one I showed earlier. In the sense, in the color scheme at least, but it's fine.
oh yeah, I suppose so. But anyway, this is from the paper, right? And the red area is the direction that we're headed toward, and the blue is where we're receding from. And then the direction of where the direction of the cosmic microwave background is almost directly in the center. There's a little dot that's to the right and down a little bit from the center of the
Right
graph.
there. C and B. You guys can see it. So
So
what is this? What is this dot saying? This dot. Yeah.
you mean the dot that's labeled CMB.
Yeah. What does
So
that mean here in the context of this diagram?
so when we say that the peculiar motion of of our solar system toward the CMB is 370 kilometers per second, that's the point it's directed at. Okay, so
370 kilometers per second. It's saying, hey, we're like, say, like you're saying we're like the blue place, and so we're supposed to head towards the dot, like according to CMB.
So we're heading, we're relative to the CMB, we're heading toward that dot in the middle, okay, or near the middle. Our direction relative to the quasars is toward the red area.
Right here.
There's a red, yes, that's our direction. And they're almost 90 degrees apart. And also our direction, our velocity relative to the quasars is about 4.5 to almost 5 times as big as the peculiar velocity of the solar system relative to the CMB, or 1,700 kilometers per second. And this is a big problem. So they should be the same.
How is this like? Is this just? How is this only recently discovered?
I think
Did we not have enough
I
data?
can't.
Maybe
I think it's just I think there were some indications of it earlier, but indeed this is a result that's been pulled out of the quasar data. So basically you could think of it as two cosmic yardsticks. Actually, I want to make sure that we're clear, because I feel like I'm kind of muddy in my expression here. The velocity relative to the CMB is 370 kilometers per second toward that point. Our velocity relative to the quasar population is near that red point, there. They're different, and our velocity is much, much bigger. Now, it could be that somehow the quasars have some peculiar motion relative to the CMB, and we wouldn't know the difference. But so these are two vast distribution of quasars, and that's kind of like the reason the quasars are important is because that's sort of the earliest signature of normal matter in the universe.
Yeah, I mean, as we
So
can see
see,
here,
and they
cosmic
kind of I wanted to say that
quasars,
yeah
galaxies.
they represent the burning flame of the contemporary universe, galaxies and structures. So so if this
Fabulous.
lambda CDM model, this lambda is the something called it contributes to this cosmological principle, which is that it's smooth and isotropic on large scales. Both of these reference frames should agree, but our motion, or I should say, our peculiar velocity should be the same, but they're not. And according to this paper, it's a paper by a guy named Singhal in the monthly notices of the Royal Astronomical Society. The dipole measured from the quasars doesn't match the dipole from the cosmic microwave.
And
Yeah,
for more information, I might just start emailing him. So, it's right there. All right, continue. Sorry.
I'm sure you'd get some, get some kind of answer. So,
Yeah,
and I want to point out that this difference isn't trivial. The motion relative to the CMB is about 370 kilometers per second. Motion relative to the quasar shell is 17. What did I say?
Amplitude of the particular velocity is by at least
1700 kilometers per second.
Yeah.
And it's not trivial, and they're at different directions, almost 90 degrees apart, and it's large enough to challenge the assumption that the universe looks the same in every direction. When we measure our relative motion, we find that the solar system.
I know I should know this maybe, but like you keep mentioning like peculiar. Like, is that a technical term? Peculiar velocity.
Peculiar is a technical term. I did try to outline it at the beginning, but it doesn't mean peculiar in the sense of strange or anything. It means peculiar to. So it's just a term of art or term of phrase that somebody came up with. It means peculiar to, or your own, possessing the velocity that you have relative to something else.
It's just relative velocity in this case. So peculiar.
Yeah,
it's relative velocity to the CM. To the
CMB.
CMB
right.
dipole,
and
yes.
It's about 370 kilometers per second toward the constellation Leo. And by the way, it's about 800,000 miles per hour, if you wanted to know. When astronomers measure our relative motion to the quasar distribution, they get something dramatically different. And so, it's and some surveys the direction is tilted. It's not perfectly aligned with the CMB. So it's tempting to shrug, maybe it's just an error, and indeed there's a lot of possible sources of systematic error. It could be that regions of sky are obscured by our own galaxy, and this paper I think goes over all of those things, trying to cover all the possibilities of why this isn't the case, because it is pretty hard to understand. Maybe dust contamination or selection bias, and all those things could warp the measurements. But the problem persists even as surveys have grown larger and more sophisticated, and new catalogs, new telescopes, different wavelength bands. This is a kind of tension that keeps showing up, and it matters. So the reason it matters.
Go ahead.
Yeah. The reason it matters. This is figure 4?
Yeah, like
what you're showing
all of these what's the difference between figure 1 and figure 4 here?
Okay, so figure 4, what he did there was they did a kind of synthetic model of the distribution just to test their various theories for why it might be wrong. And so the fact that the gross behavior of these two is the same, validates their measurements. So this is a model of the distribution.
Okay, I can see here where it says simulated.
Yeah.
Something mg smaller than 20.5 redshift data.
Yeah. Yeah. So I don't know that the model is really all that important, except that he's just trying to show that the assumed behavior is more or less is grossly consistent with the observations that he's making. So it's that's always a good thing to show. So the two, but so the CMB result and the quasar result are separated by billions of years of cosmic history, and so they show something that's dramatically different. And so it's kind of pointing to the idea that something fundamental might be off. So if you think of it like this, suppose you have two perfectly synchronized clocks, one made at the beginning of time and one built billions of years later, and they don't agree. You start to wonder whether time itself is running differently than you thought. Or suppose you're on a ship in the ocean, in the open ocean. You can check your compass and it says you're sailing east 20 knots. Then you look at the stars and they say you're only moving 10, and maybe in a different direction. So that's the metaphor or analogy of what we're wrong. It's of what the concern is. It's you have to ask, maybe the compass wrong, or maybe the ocean itself is moving, right? So it's a puzzle that we're facing. And the light of the cosmic microwave background comes from when the universe was less than 500,000 years old. It's the first visible glow of creation. And the light from quasars, yeah.
Okay. Is this just a different projection in Figure 5?
Yes, right. So he's just further validating that point.
This is relative to the center of the quasar, right? Yeah.
Okay. So anyway, if the quasar frame and the CMB frame truly diverge, it means the universe on the largest scales may not be static in the way we imagine. I mean, think about it. I mean, it's like we see two different velocities, and it's really hard to figure this out. Either way, the discrepancy hints at something deeply unsettling, that the universe might not have a single universal rest frame after all, and that the cosmic backdrop we thought was fixed.
Yeah.
It could be shifting under our feet. The question then becomes why? Is it an illusion of measurement on real physical motion on scales larger than we've ever mapped? And it could be evidence that the lambda CDM model, which is our best description of the cosmos, is missing something. So anyway, so the possible explanations, we could be, might be, there could be systematic effects, which are kind of like the ordinary culprits. Maybe there are small biases in how we collect and interpret the data. These catalogs where the quasars are recorded are built using light collected through the Earth's atmosphere or by satellites scanning specific patches of sky. Our own galaxy, the Milky Way, blocks large regions with dust and gas. And to avoid confusion, astronomers sometimes mask those areas, which means parts of the sky are literally ignored. That uneven coverage can create artificial patterns. So that's really something that they need to look at very carefully. There's also selection bias. Brighter quasars are easier to detect. The brightness itself is affected by the redshift, by distance, and by gravitational lensing, which we talked about in the past. If the data set contains slightly more bright quasars in one direction than in another, it could mimic motion where none exists. So there's plenty of technical reasons why the quasar frame might appear offset from the CMB frame. So and I think actually the reviewers of this article that we're talking about and a lot of critics think that's actually what's happening, is that there's some kind of
it's just poor interpretation of data. Basically.
Well, I don't want to call anybody
maybe I shouldn't
poor interpreting. Just I'm saying that some kind of error that we haven't thought of. The paper I think is excellent, right? So it's not not like there's anything to criticize there. But the simplest physical explanation is that the universe itself is moving not as a whole but in parts. In other words, somehow we have different we have bulk flows, and so that's an interesting possibility. So
fascinating.
There's a more radical possibility.
What is a more radical possibility?
Well, the cosmological principle, which is the cornerstone of modern cosmology, says
All
that
right,
on large scales, the universe is
cosmological principle.
yes, that it's homogeneous and isotropic. But what if it's not true? If the
What
universe even
if
has
it's
a
not true?
yeah, a built-in
Okay,
asymmetry.
okay. Cosmological. Oh wow, I need to take a swig of water too. Uh, States that no matter where we look in the universe, we see the same distribution. Since the universe at large is homogeneous, or right? So,
Yeah.
or isotropic, I
So
should say. Yeah.
so it's a fairly recent. This is a fairly recent paper, and it's attracted some attention, and it seems to be important to me. So there's some kind of new physics beyond that lambda CDM model. Our standard picture of dark energy, dark matter, and cosmic expansion may be incomplete. And maybe
Okay.
the assumptions of uniformity and statistical symmetry break down on scales larger than we can see. Or maybe the dark energy isn't perfectly uniform. That could do it also.
What would this
So,
what would this imply for our existence?
well, it would imply, I don't know that it has anything to do with um, a- any kind of any kind of
All right, fine. It's not.
anything to do with
We're
our
gonna keep
existence
living.
exactly. Yeah, I think we're okay, but it
We're
is a
fine.
profound it is a
Okay.
very profound challenge to
Yeah,
our
I hear that.
understanding. So okay, so it I think it's important in science. We're used to mysteries resolving themselves with better data. The messy edges smooth out and numbers converge. The puzzle dissolve. Sometimes they don't, and that's what's going on here. Sometimes the anomaly survives every correction, every reanalysis,
Can
every time every reanalysis, every survey, and when that happens, the anomaly stops being noise and starts being a clue. I think
right.
we're at that stage now. Okay, the
So
disagreement between yeah,
okay, go on.
I was
Sorry.
going to say the disagreement between the CMB and the quasars may turn out to be one of those clues. It's a small, stubborn crack in the cosmic mirror that reflects our assumptions about the universe. I mean, obviously, that's the case. So,
I mean,
um,
most things are like this, right? Like you start out with having small
hmm
things, well, quote unquote, small evidence that doesn't seem to fit the prevailing theory, and then it
that's
turns
right.
out that it's just the start of a flood that shows that the
That's
prevailing
right.
theory is incomplete or incorrect.
So,
Um,
so
so you keep, oh, sorry, you mentioned lambda CDM, right? Or is it
Uh-huh.
several times?
Lambda,
What is that?
the lambda is the cosmological constant that Einstein introduced in the equations to explain why the universe doesn't collapse, and so that's mainly basically that's our dark energy component, and then the CDM just means cold dark matter. We think that there's a lot of dark matter that's dominating the motion of the universe. So that's kind of it's almost like a standard model, right? So
Okay.
so if I step back from the numbers for a minute, just what does this motion mean? Um, in everyday life, motion is simple. You move relative to the ground. The plane moves through the air.
I'm
The air
moving right
moves through
now.
the
Let's
Earth
say
rotation.
moving.
Each layer has its own reference point, but the idea of absolute rest never really appears. We usually don't notice this because our senses, give us a local illusion of stillness. The floor beneath us feels solid. The stars above seem fixed, but in truth, everything is in motion. So we know the Earth is spinning, the sun drifts around the Milky Way, as we pointed out, and so forth. And now we learn that even the universe's own frame of reference might be shifting. So that's the big point there. In other words, we measure our motion relative to the CDM, uh, the CMB,
The
right? And
CMB
then we
cosmic
measure
microwave background.
and then we measure it relative to um, a, a, a a shell of quasars that are very far away, and we have a drastically different motion. So it's it's an almost existential question. If everything is moving, including the yardsticks we use to define the motion, then the motion itself becomes relative, not just in physics, but kind of, I hate to say it, but kind of in the philosophical sense. There's no fixed background, no cosmic zero, only relationships between things. So the cosmic microwave background once seemed to give us a 0 point. It was a great ocean, quiet ocean of ancient light.
Right.
Right.
We thought the cosmic microwave background could, even though we know there is no like absolute reference frame, we at least thought it's the closest we could get to. But even now, that seems to be like,
so.
Shifting.
Just reflecting on this picture that you have shown up here. I mean, it's a big problem because it means that the quasars are moving with a bulk motion relative to the CMB or something like that. Okay, and so it's something that needs to be resolved. I think so. It hints that even the universe's deep patterns aren't perfectly aligned. That the past and the present may not even agree on what rest means. So that we have two different rest frames. Maybe the universe is reminding us that motion is not a defect or an illusion, but a fundamental property of being. That's pretty staggering. So everything that exists in flux, right?
Yeah. So like,
right?
That would make sense. So, I don't
Cool,
know.
huh?
That is pretty cool. It's also, yeah, I guess
maybe it's a metaphor. It's a metaphor for our own condition.
A metaphor for our own condition comes from the breaking of what, like the CMB as that, like an absolute standard of where we.
We too live in between frames, between the ancient light of where we came from, and the luminous galaxies of where we're going. Maybe it doesn't seem like they perfectly align. Perhaps there's no universal rest frame because the universe is still becoming. It's still unbalanced, still unfolding. I actually do buy into that. Okay, and we drifting through it hundreds of kilometers per second are part of the motion. So. Anyway, the unfinished question, so I don't know, like, where does it leave us?
I mean,
how fast?
It's not like the paper has a. Let me see if I can. It did have a resounding conclusion. Let me put it that way.
Well, it's really just short. A phenomenological. It's a short paper, right? It's a short paper.
And I found it interesting that the author fully admitted he got no funding to do this research. Which is great. So
that's wonderful.
Do it on your how's that wonderful? You just do it on your own time.
I mean, I can see. I don't. It's not. I don't think it's that difficult to do this paper because he had a lot of it. He evidently has experience with the catalogs.
Yeah.
And he could just do the. You can just use the spherical harmonics to pull out the dipole field.
Anybody could get the data, and assuming you have enough math, and assuming you have some basic math knowledge and some astronomy knowledge, you could do this. Like, I could do it.
I think so. I guess I could do it. I don't have the knowledge about where the data sets are and all that kind of thing. But it's kind of a simple result.
I'm sorry, this is a weird diagram. What is this ones and twos here? It's like, what is going on?
I don't know. I didn't. Yeah.
Oh, okay. Hemisphere sigma 1, center about the galactic center. All points in the hemisphere sigma 2. Oh, the galactic center. Oh, it's showing the center and the anti-center. Okay, symbol 2. All right, never mind. But all right. I'm not going to read this whole research paper right in the middle of the audience here. But the point is the conclusion. What does the conclusion say? It says this.
Well,
a redshift anisotropy, which note means not uniform, the opposite of isotropy, A large all-sky sample of 1.3 million quasars has yielded a solar system peculiar velocity, which is 4 to 5 times larger than the peculiar motion inferred from a dipole asymmetry in the CMB. Even
Yeah.
more curiously, direction of the inferred peculiar velocity within 1 sigma coincides with that of the galactic center.
Correct.
Of
right.
course, it cannot be ascertained whether we're moving with a large speed of 1,700 kilometers per second toward the Milky Way center, or is it the whole Milky Way galaxy, perhaps part of a larger system that is moving in a direction which is seen from a vantage point on Earth, happens to coincide with the Milky Way center. In either case, the peculiar motion derived from the observed asymmetry in the redshift distribution of 1.3 million quasars in the sky does not seem to agree with the derived conventionally from a CMB dipole asymmetry, a result which is not in accordance with the cosmological principle, a cornerstone in the basic foundation of the standard model in cosmology.
I couldn't say it better myself.
I mean, I said it pretty well, but
Right.
that's because I can read.
Because you read the author's conclusion.
I can read so well, you know.
Uh-huh.
It's like, okay. Oh my God.
Anyway, that's kind of all I wanted to say about this. I think we got the point across that there's something fishy about. I don't doubt these measurements, but it's really begging to be studied and understood. Solar peculiar motion. It isn't just about velocity. It's about perspective. You know, it reminds us that every measurement we make, whether stars, galaxies, or even truth itself, depends on where we are standing. And yet, in the middle of all that relativity, there's something oddly grounding. We may never find a universal center, but we can still locate ourselves.
You know, that sounds so
Okay.
beautiful. I actually want to almost
Nice.
read this.
Okay.
Typically we start out the show by like me reading a poem or something, right?
Well,
And
okay, sure.
okay, I want to finish it up by reading a poem about motion,
All right.
actually, and all that.
Do it.
So, but do we have more to say? How much more do we have
No.
to say here?
I think we got it all. I think
you sure?
I think we've reviewed this article. I think
To the degree,
yeah.
yeah.
mhm. So
To the degree that it you know, I am curious if anybody else out there in this world has actually gone through and done an active discussion on this article like we have. This might be unique. So, in other words, guys, people watching, you're unlikely to find another podcast or video out there discussing this particular article or this particular phenomenon as it stands right now.
I don't know of
confidently say
any.
that.
I don't know of any, but so anyway, so we should be grateful. We've got this cool thing to talk about, and we've scooped everybody. So
Yeah.
the best way to end the story is not with certainty, but with gratitude. For the we live in a universe still full of motion, still full of mystery, and still willing to surprise us.
That is so true. And with that, let me just read this poem very briefly that I wrote a little while ago.
Go for it.
I know, Leonard, I invited you to the poetry event, but this could be one for our universal audience out there. So let's do this. I'll keep you on here.
Okay.
So this is what I wrote one day when I was thinking about what to do sitting on a weekend which had no concrete plans. And then I thought about motion, which is related. All right, I'll just read this. On a day with no concrete plans, infinity stretches in front of me. If I'm not careful, the infinite can converge towards zero. There's an lure to hiding from this world, standing still. But form can be anything, yet it's pure chaos without structure. Just like the earth must rotate and revolve, so too my life cannot be a frozen state in space-time. But if there's no laws of physics curated, coincidentally or by providence, to have an appropriate rotational rate for day and night to coexist in life-affirming quantities, an appropriate average distance from the sun to not boil or freeze this planet, an appropriate eccentricity to the orbit, and a slight tilt to the axis of rotation to have reasonable seasons, life without physical curation would be dead. So I asked myself a simple but hard question. In the name of freedom, I can do anything I want, but to offer my existence greater meaning, to fully enter my essential self, to build towards the future knowing the past, where do I fling myself today in a state of change, bounded to affirm joy, unbounded to affirm freedom?
Wow.
Yeah.
Well done. Okay.
Thanks.
Anyway.
But
Anyway.
did not mention the cosmic microwave background or the fact that our, whole Milky Way is moving.
It's all good.
But the point
Anyway.
is, philosophically, everything's in motion, including people's lives. And you gotta, that's
kind of what I think.
nothing,
Yep.
There's nothing that can stand still.
All right.
So with all this said, thank you for all our viewers. For instance, wow, apparently Shiny Nichols is posting a lot, so I would just say thank you. Lindsay, I believe that's who you are. If I'm mistaking you for somebody else, I'm sorry. Thank you then. So, alright. But for all other viewers out there who may not have posted comments, feel free to post a comment later.
Yeah.
Or at least like, subscribe, and share this. So that, it'd be always interesting to hear what people think. If there are, I'm going to say this, since this is going to be interesting. If there are other research articles you guys find out there, please feel free to let me know. Let us know. Drop a comment or something.
That's a very gracious invitation there. I really like that. Yeah. If our audience has some topic that they'd like us to cover, otherwise we'll just keep thinking of things. I mean, we don't have any trouble.
It doesn't have to be a research article, but if you happen to find a research article like this one, or just some other topic that you feel like hasn't really been covered by us or really by anyone, then we'll see if we can do it. So, yep.
All right.
Appreciate all our supporters. Thank you for the name, John Graves, Kyle Baker, George Jackson, Geoffrey Barnes, and anybody else who is actually actively supporting us or in whatever capacity. With all that said, we will be back. So if this time works for Leonard, we can do it again next Thursday.
Okay.
That's if you're watching it live. So we will come back with another, I'm sure, exciting episode. So
yeah, you
all
betcha.
right, everybody. What? And what is
Say
this?
namaste.
Namaste.
Yep. And shalom and thanks.